naming the supercontinent of galaxies, Laniakea. If you want to know where you live, you don't start with a dot, you start with the currents around it. That's what the Cosmic Flows teams did. They took thousands of galaxies with carefully measured distances and redshifts, subtracted the universal expansion, and watched where the leftovers, peculiar velocities, actually go. Then they did something deceptively simple. They followed the arrows. Picture a relief map where elevation is gravity's potential. High ground is sparse, low ground is dense, and rivers are galaxy motions. When they traced those streams, the lines didn't end at the bright beads we already knew. Virgo, Centaurus, Hydra. They converged into a broad gravitational low centered near the Norma cluster. Flow lines from hundreds of millions of light years away sloped down toward the same basin. Boundaries emerged the way watersheds do. If a galaxy's motion descended toward Norma's lowland, it belonged to our basin. If it spilled the other way toward Perseus, Pisces, or Coma, it didn't. That's when the name arrived. Laniakea, immense heaven in Hawaiian, wasn't just a label. It was a statement about how to draw the map. Instead of carving the sky into boxes by brightness or guesswork, they used dynamics. The numbers are staggering. Roughly 500 million light years across, about 100,000 large galaxies, and on the order of 100 quadrillion suns of mass stitched through filaments and clusters. Our local group sits out on the basin's shoulder, a tributary feeding inward. The Great Attractor is the low place, not the sovereign, an emergent feature in an uneven landscape. A micro-story from that moment says more than a plot. In a conference room, the flow map came up on the screen, a sea of white arrows bending like a time-lapse of winter winds. Someone dimmed the lights. A senior astronomer traced the ridgeline, where flows split and circled the low. "This," they said, "is home." The room was quiet because home just got bigger than anyone was used to saying out loud. Emotionally, it lands like seeing your neighborhood from above for the first time. We've spent a century naming ever larger structures, cluster, supercluster, but this felt different because it moved. You're not in a pile, you're in a river system. The stakes shift with that view. Boundaries by watershed mean that the Milky Way shares its address with galaxies you'll never see again after a few tens of billions of years, because cosmic acceleration will stretch the larger map. Within Laniakea, gravity still guides the flows. Beyond, dark energy draws the coastlines apart. Technically, the watershed approach solved problems that had nagged for years. Why did the old, local supercluster box miss obvious connections? Because light alone can lie to you. Dust hides, X-rays bias toward hot clusters, infrared misses quiescent ellipticals. Velocity fields don't care what shines, they care what weighs. By reconstructing the three-dimensional pattern of motions and inverting it into a gravitational potential, researchers could identify the true basins. The Norma Centaurus Hydra region defines Laniakea's core, not because it's prettiest, but because the arrows say so. There's humility built into this. Laniakea is not gravitationally bound as a whole. On the longest scales, dark energies push winds. The basin stretches, and only the deepest wells, clusters like Virgo or Norma, stay coherent. But for now, the flows are real. Our kayak points downstream. If you run the movie forward, our local group merges with Andromeda in a few billion years, drifts deeper into the basin's influence, and yet, in the far future, watches most of Laniakea slip past the horizon. The name holds both truths, immense heaven and finite sight. Meanwhile, this mapping opened the door to the next twist. When the team extended the flow reconstructions beyond the basin, the arrows didn't stop at the Great Attractor's floor. Some bent farther, toward the Shapley concentration, a massively overdense district like a range beyond the valley. Others seemed freer because, behind us, the terrain sits higher and emptier than average, letting matter slide away. In that geometry, pull and push aren't rivals. They're two sides of the same slope. So we have a gravitational supercontinent with rivers you can chart and a name you can say. But the ground under our feet is moving, and there's a heavier range waiting downriver. The map just got bigger again. Shapley, the heavyweight beyond. While the basin at Norma explains why our local arrows bend, the deeper pull sits farther downriver. Astronomers had hints decades ago, beyond Hydra, Centaurus. Redshift surveys sketched an extraordinary overabundance of clusters gathered across a few 100 million light-years. They called it the Shapley concentration, after Harlow Shapley, who mapped the sky's large-scale structure before we had computers to carry the load. Think of it as a mountain range past the valley floor, a stacked complex of clusters whose combined gravity can reach across Laniakea and tug on our entire basin. Here's where numbers stop being intuitive. Shapley isn't a single cluster. It's a thicket of them, with masses that together rival or exceed anything comparable within 1 billion light-years. Its densest knots glow in X-rays, from gas-heated to tens of millions of degrees. Optical surveys count galaxy after galaxy in tight packs. Peculiar velocity reconstructions that include those depths change the story. The Great Attractor becomes a way station, not the final destination. The flow lines that dive through Norma keep leaning, past the basin's low, onward toward Shapley's greater weight. A stakes moment arrived when teams fit our local group's 600 kilometers per second motion with multiple contributors. Virgo provides a slice. The Norma Centaurus hub adds more. But to match the amplitude and direction of the CMB dipole and the galaxy flow field, you need a long-reach term. Shapley's mass supplies it. That's the pull-through story. The Great Attractor isn't a sink that ends the journey. It redirects you, like a gentle saddle, aiming you toward the dominant mass beyond. If you could paint the gravitational potential from our vantage, you'd see a subtle downhill toward Norma that tips more steeply toward Shapley's ridge. Action moved from catalogs to reconstructions. Cosmic flow-style inversions that extend their volume farther into the southern sky show the streamlined geometry change character as you pass Hydra Centaurus. Lines that fan inward tighten and align toward Shapley's core. When you separate contributions in the model, mask Shapley, and watch the residuals, the predicted local motion slumps. Put Shapley back and the vectors recover. Different datasets tell the same story. SNEEA, distances, surface brightness fluctuations, Tully, Fisher measures. The specific weights vary, but the pattern doesn't. Shapley matters. Meanwhile, the zone of avoidance plays a quieter role here. We don't see Shapley through the Milky Way's midplane. We see it around the edges where dust thins. That's fortunate. Clusters like Able 3558, 3562, 3556 light up cleanly enough to anchor mass estimates. X-ray temperatures, galaxy velocity dispersions, weak lensing signals, each one a ruler on the same scaffolding. Stack those rulers, and you get a mass that justifies a long-arm tug. The uncertainties live in the outskirts, where filaments feed the core. But even conservative bounds leave Shapley as the southern sky's heavyweight. A micro-story captures how the picture clicked. In a small office, a researcher ran 2 reconstructions back-to-back. First, they truncated the data at Laniakea's edge. The flow field curved into the Norma basin and settled. Then they added a deeper shell with Shapley's clusters and resolved. The basin's floor tilted. Arrows that had relaxed reoriented like iron filings under a magnet nudged to a new angle. They printed both frames and taped them up. This is why the dipole points where it does, they wrote under the second. It wasn't poetry, it was relief. Debate followed, the good kind. How much of our motion is locally sourced versus long range? Does the Great Attractor contribute half and Shapley a third, or vice versa? Different teams landed on different splits depending on distance ladders and masks, but the consensus held. You need both. A dense valley ahead and a denser range beyond. Fold in the emptiness behind, the dipole repeller's underdensity, and you get the full geometry of our drift. Less resistance from the rear, a nudge from Norma, a steady pull from Shapley. Why this matters scales beyond cartography. When we calibrate the cosmic distance ladder, bulk flows bias the steps. If you set Hubble's constant using galaxies streaming toward Shapley without correcting their peculiar velocities, you skew the result. Mapping where Shapley sits and how strongly it tugs cleans those biases. It also refines models of structure growth. Simulations under LOSA CDM need to produce Shapley-class concentrations with the right abundance. They do, but the details, feeding filaments, merger histories, are tests you can only run with a precise map. There's a human beat here too. A student staring at a wall-sized plot of streamlines traces the long curve from our local group to Shapley with a dry erase marker. Then steps back and laughs. Not because it's funny, but because the path looks like something you could hike if you had a few billion years. Across the hall, someone sets a small sticker shaped like a kayak near our dot. It stays there through 3 Grant cycles. The joke wears into a reminder. We're not just falling, we're being steered by terrain we can now describe. So Shapley is the heavyweight beyond, the range that bends the whole watershed. The Great Attractor guides us toward it. The empty highland behind makes the slide easier, and dark energy stretches the map while all this plays out, which sets up the next tension. If gravity can organize rivers at these scales, how far does that coherence reach before the accelerating expansion thins everything out? The rumor mill called it dark flow. The data has stronger, subtler answers. Dark flow or data mirage? While Shapley loomed ahead and an emptier highland trailed behind, a louder claim hit the field. Maybe the whole observable patch of galaxy clusters was sliding in one grand direction, a motion so vast people called it dark flow. If true, it would hint at influences beyond our cosmic horizon, structures we can't see tugging our entire sky. The stakes were enormous. Either we'd mapped a subtle, local river, or we were feeling a tide from outside the charted ocean. The evidence came from a clever lever, the kinematic Sunyaev-Zeldovich effect. Hot gas in galaxy clusters scatters CMB photons. If the cluster has a bulk velocity toward or away from us, the scattering imprints a tiny temperature shift in the CMB at the cluster's position. Doppler fingerprints of motion riding on ancient light. In principle, stack enough clusters and the random noise cancels, leaving a net flow vector. In practice, the signal is tiny and the foregrounds are noisy. A team reported that stacking hundreds of clusters revealed a coherent drift extending to at least 800 million light-years, roughly aligned with the CMB dipole. They called it a dark flow, and for a moment the room spun. If a flow that large held up, local basins and repellers weren't the whole story. Something beyond our horizon, or a departure from standard cosmology, might be pulling. Then caution kicked in. The method sits on a knife edge. You need exquisite control over cluster profiles, beam systematics, and CMB foregrounds. Misestimate a cluster's gas temperature or mishandle microwave backgrounds, and you can conjure a velocity where none exists. Independent teams reanalyzed the stacks, swapped catalogs, tweaked filtering. Some saw the signal shrink, others saw it vanish within errors. Planck's all-sky maps, with better frequency coverage to separate galactic dust from the CMB, found no compelling evidence for a coherent, suprahorizon bulk flow. The case for a universal drift weakened. Meanwhile, other approaches to large-scale flows, type Ia supernova distances, peculiar velocity reconstructions from galaxy scaling relations, and velocity correlation statistics, painted a quieter picture. Yes, there are bulk flows on scales of a few hundred million light-years. Gravity from structures like Shapley, Perseus, Pisces, and the Sloan Great Wall can do that. But when you push to the very largest scales, the flows damp the way LoveCDM predicts. Large, but not law-breaking. A micro-story captures the turn. In a corridor after a conference talk, a postdoc balanced a coffee and said, "I want the dark flow to be real." The senior scientist smiled. "Want isn't enough. Show me a signal that survives Planck." Months later, the same postdoc presented a null result and shrugged. It's beautiful without it. What survived the fire drill? 2 things. First, the KSZ technique works. With better data and modeling, it measures cluster peculiar velocities, just not a cosmic tide from beyond scale. Second, the dipole repeller and attractor picture, the push-pull within our volume, fits a wide array of independent probes. You don't need an external hand to explain why the CMB dipole, local galaxy flows, and Laniakea's basin line up broadly. Gravity and emptiness inside the horizon suffice. That doesn't make the episode wasted motion. It refined our instincts. Extraordinary claims, flows that rewrite boundary conditions, demand cross-checks with independent messengers. It also sharpened the idea of coherence. The universe can host extended flows over hundreds of millions of light years without violating the standard model. Those are what you get when adjacent basins share slopes and ranges. But coherence isn't uniformity. Beyond a certain scale, velocities decorrelate, and the Hubble flow dominates. Technically, the dark flow saga improved tools we still use. Better cluster catalogs, multi-frequency foreground cleaning, improved beam calibrations, and stacking techniques all feed into today's KSZ measurements of growth and bias. The null leaned us away from exotic pulls and toward the terrain we can map. The river is wide, not infinite. So was it a data mirage? As a single, horizon-spanning current, yes, so far. As a warning that our instruments and methods can conjure tides from ripples if we're not careful, also yes. Meanwhile, the live story remains richer than either extreme. Our kayak moves under real, measurable influences. Valleys ahead, sparse plateaus behind, woven into a fabric that accelerates. The next question isn't whether a hidden ocean steers us. It's what the accelerating sea does to every river we've mapped. The three endings: heat death, big rip, vacuum doom. We followed the river through basins and past ranges, but the river runs on a planet whose shoreline is moving. Dark energy, the term we use for whatever drives the accelerating expansion, sets the long fuse. Gravity writes local stories. Dark energy edits the ending. Three drafts keep showing. Up when cosmologists push the math forward: heat death, big rip, and vacuum decay. Each is cold comfort. Each answers a different version of the same question. What wins when expansion, quantum fields, and gravity pull in opposite directions? Start with the quiet one: heat death. In this draft, dark energy behaves like a cosmological constant. Its density stays roughly the same as space grows. Galaxies beyond our local gravitationally bound group drift out of reach, their light stretched until it never arrives. Stars burn out. New stars grow scarce as gas thins. Black holes eat the leftovers and over unimaginable spans evaporate by hawking radiation. The night doesn't end in a crash. It thins into a gray, cold fog of low-energy photons and particles. Entropy, the universe's tally of ways to be disordered, maxes out. There's no free energy left to do work. In a heat-death cosmos, the Great Attractor's basin matters for a while. We and our neighbors merge, settle, and keep each other company. Then the horizon closes, the lights dim, and the river becomes memory inside a lonely island. Now the loud one: big rip. This needs a twist in dark energy's character. Its pressure must be more negative than a cosmological constant. A case physicists shorthand as W-1. That phantom energy makes expansion not just accelerate, but accelerate faster and faster. Gravity loses territory. First, superclusters unbind. Later, individual galaxies. Later still, solar systems. Far closer to the final seconds, stars, planets, and finally atoms themselves can't hold together. The schedule depends on how far below -1 the equation of state parameter sits. At W just shy of -1, the rip is never. At world noticeably less than -1, timelines people quote are tens of billions of years from now for galaxies to peel apart, then cascades closer together. Millions of years for solar systems, hours for planets, fractions of a second for nuclei. It's a script with an ending you can circle on a calendar if you knew W exactly. We don't. Current observations: supernovae, baryon acoustic oscillations, the CMB, cluster around W or equal to -1 with small error bars. That keeps the big rip on the table as a theoretical path, but not the favored one. Still, the image lingers. An expansion so insistent it shreds the very bonds that made the river possible. Then there's the trapdoor: vacuum decay. Here the villain isn't expansion. It's the idea that our universe's vacuum might be metastable. In quantum field theory, a field can sit in a false vacuum, a local minimum that isn't the absolute lowest energy state. If a quantum tunneling event or rare fluctuation kicks a patch into the true minimum, a bubble forms where the laws inside can differ. Particle masses, forces, the whole rule book. That bubble would expand at near light speed, rewriting physics as it goes. There's no warning, no causal signal outruns the edge. One moment you're in a universe with chemistry. The next you're in one without familiar atoms. It's not an explosion you can survive. It's a clean edit. The saving grace is that calculations tied to the Higgs field, and our best fit parameters suggest either stability or lifetimes. So long they make heat death look impatient. But the possibility sketches a different kind of end. Not running out of fuel, not ripping apart, but a sudden cut to a new scene. Stakes for us sit between these drafts. In heat death, our local island, the remnant of the local group and any friends we catch before acceleration wins, becomes the whole sky. The basins we mapped flatten into solitude. In a big rip, Even the island dissolves. The Great Attractor's terrain is a chapter, not a climax. In Vacuum Decay, the map doesn't matter, the bubble doesn't care about flows. Meanwhile, the data favors the quiet ending for now. Measurements of W flirt with -1, and every new survey, supernovae standardize better, large-scale structures map deeper, gravitational waves tuned as distance rulers, tightens the leash. The odds shift toward a cosmological constant and a long fade. But a decimal place matters. A small tilt below -1 rewrites the timetable. The uncertainty is honest, not theatrical. There's a human micro-story folded into these endings. A graduate student in a late-night seminar sketches 3 horizon lines on a whiteboard. One closing slowly, one racing outward, one erased by a bubble. They write Laniakea on the first, Shapley on the second, then circle both and add local in the margin. The professor nods. Our river is a local story. The ocean's climate decides the season. That sentence holds the paradox. We can map our slide into a basin. We can feel the push from an empty highland and the pull from a range. And we can still be honest that the larger weather, the equation of state of dark energy, the stability of the vacuum, sets the horizon's pace. So choose your draft. A long, quiet dimming, a catastrophic unbinding, or a clean cut. Each says something about what erasing means. Not deletion, but separation. Not a villain swallowing us, but a boundary moving past what we can touch. The river runs on, even if one day from here it looks like the world ended. Dark energies vote, what the data says. If the river is local, the climate is set by one parameter. Cosmologists call it W, the equation of state of dark energy, defined as pressure divided by energy density. It's a single letter with oversized consequences. If W equals -1, dark energy behaves like a cosmological constant, steady, uniform, patient. If W dips below -1, phantom territory, expansion accelerates faster, and the big rip creeps from theory toward schedule. If W rises above -1, acceleration can ease. The universe has cast a ballot. Our task is to read the tally.